W1.2, polarisation. Polarisation is something that only works for transverse waves, and that's because you have to have the oscillation at 90 degrees to the direction of travel. So in this diagram we've got something like a rope or a rubber cord which is oscillating up and down, in and out of the screen, and any other way at 90 degrees to the direction of travel. So it hits a filter, which in this case is a board with a slot cut in it, and this first slot is vertical. So it will allow vertical parts of the wave through, but any part that's oscillating horizontally will get blocked. So in the middle of the diagram here, this wave is now vertically polarised. It's only oscillating up and down. It then hits the second filter, and this time the slot is arranged horizontally. So it would allow horizontal oscillations through, but there aren't any because the wave's already been polarised, so nothing gets through. Light is a transverse wave, so in this diagram we have the light travelling in a straight line towards the first filter. What you can't see is that it is actually oscillating up and down and in and out of the screen. Hits the first Polaroid. Its orientation is marked by the little stripy corner here, but let's say that this allows vertical oscillations through but not horizontal. So in the middle of the diagram again we've got polarised light, so it's just oscillating up and down vertically. This next Polaroid filter is rotated by 90 degrees, so it would allow horizontal oscillations through but not vertical, and since the polarised light is oscillating vertically and this only allows horizontal light through, you won't get anything. So if you were to look through these two crossed Polaroids, you'd just see darkness. Now most light from the sun or light bulbs is unpolarised. It's oscillating in all directions, but there are circumstances where it can become polarised, and one is by reflection. So imagine you've got the sun and some sort of shiny surface here, which it could be a surface of some water like a swimming pool or a lake, the sea, or a plastic surface or some shiny paint, something like that. And you're looking at the surface and the light from the sun is coming down, hitting the surface and reflecting back up into your eye. So you see the reflection of the sun. And the light on its way to your eye, as it goes towards the surface, is oscillating at 90 degrees to the direction of travel, so it's up and down in this diagram, and also in and out of the screen, which is a bit difficult to represent on a flat screen. But I'm going to draw these circles. So the circles represent light going in and out of the screen. Now the bit that comes up towards your eye is polarised, because the bit on this side, which is going in and out of the screen, when it hits the surface and bounces, can still go in and out of the screen. It's still at 90 degrees to the direction of travel, and it can happily make its way up towards your eye. But the bit of the wave that's going in this direction, when it hits the surface, it can't travel up towards your eye, because that would then be in the same direction as the direction of travel, and transverse waves just don't do that. So that part of the oscillation is blocked, and what you're seeing is polarised light. Now that can be is useful, because if you wear a pair of Polaroid sunglasses assume that most annoying reflections are coming from horizontal surfaces like water, and therefore they're arranged to block any oscillations in the horizontal direction. So this oscillation would be blocked by the sunglasses. If you were to put your head on one side so that the sunglasses were in the wrong way round, then you'd see the reflection again. This works perfectly if the the angle between the incoming ray and the outgoing ray is exactly 90 degrees. At other angles it works, but not perfectly. So in this photograph, you've got the reflection of a tree in the water. This is behaving a bit like a mirror. In this version of the photograph, that reflection has been cut out and you can see into the water. You'll notice in the top half of the photograph you can still see the reflection a bit, not quite so brightly, but that's because the angle is up here is not 90 degrees. In this photograph, in the top one, you've got the reflection of some people standing around the car quite clearly, but in the bottom half with the filter in front of the camera, they disappeared. Another way of getting light to be polarised is by scattering. So imagine you're standing on the ground on a sunny day and the sun is shining across the sky. So all that light is travelling above you, is oscillating up and down and in and out of the screen, represented by the circle once again. Now, the reason you can see the sky is because there are lots of dust particles up there, and the light will hit the dust particles and some of it will bounce off and come towards you, and that's how you see the sky. Now, the bit that is oscillating in and out of the screen here, again represented by the circle, can come down towards you because that's still at 90 degrees to the direction of travel. But the bit that's oscillating up and down here and here can't come towards you because that would be in the same direction as the direction of travel, and it doesn't happen like that. So scattered light is polarised. Now, we haven't got much use for that, but insects, particularly bees, can use that to help them navigate, because they can use it to work out where the sun is, even if the sun is not visible in the sky. The one use that we do make of it is in photography, because it can improve photographs. So in this photograph we've got a filter over a picture of the sky, and as you can see through the filter it's much bluer and deeper and clearer, making a nicer photograph. In this version we've got quite a nice blue sky here, but through the Polaroid it's bluer, sort of richer colour, and makes a nicer picture. Another use of polarisation is in photoelastic stress analysis, and that's where you observe something like a plastic specimen through crossed Polaroids, and as you can see you get these nice bands, pretty bands of colour, and where it's very stripy, where the colours are changing in a very short space, that means that's an area of high stress. The reason things like set squares look stressed is that they're made by a process called injection moulding, and the stress patterns are sort of locked into them as they're cooled and as they set. The last use that you need to know about is aerials and antennas. So if you've got an electromagnetic wave, like radio or television wave, and you're trying to pick it up with an aerial, you have to have the aerial orientated in the same direction as the incoming wave. So in this picture you've got a vertical aerial which is expecting a vertically polarised wave, so that would have been produced from another aerial around the same way. Any horizontal wave wouldn't get picked up by the aerial. The incoming wave basically makes the electrons in the aerial move up and down the aerial, creating a voltage across the ends which can be picked up and provides you with your signal. Okay, and that's it for polarisation.